Okay, good morning everyone. The Colombian Association of Petroleum, Energy and Related Technologies Engineers, ASPET, warmly welcomes you to this technical webinar, part of our ASPET Academic Initiative, a program that delivers comprehensive technical and technological training through strategic partnership that address the needs of employees, entrepreneurship, and innovation in the energy sector. We would like to inform you that a QA box will be available throughout the session. Please feel free to type your question at any time. They will be addressed by the speaker during the dedicated Q&A segment at the end of the presentation. Today, we are pleased to welcome Mr. Justin Lusowski, Director of Engineering at Valor Method, who will present this session titled Closed Vent System Analysis for Atmospheric Power. Mr. Lusowski is a mechanical engineer with 18 years of experience in the oil and gas industry and holds a master's degree from Colorado State University. His expertise brings great value to today's sessions. Now, I give you a pass so you can start your presentation.
Great. Thanks for jumping on this webinar. Let me get my screen sharing real quick. One moment.
It's okay.
All right, great. So today, I wanted to talk to you guys a bit about closed vent systems on atmospheric storage tanks for the oil field. And, as far as my presentation goes, it's really at a slant towards the US EPA in terms of that's really how we structure our approach and our engineering assessments from a regulatory standpoint. Now, there is mechanical design, fluid properties, all those things that go into how we do our analysis, but it's really focused on how US EPA views this. And so as we go through, I'll kind of be talking a bit about that and how it goes into play. So feel free to ask any questions as to the chat, and we'll get to those at the end of the presentation. Advanced. There we go. Perfect. So as we kind of go through this, from a overview, we'll talk about CVS. So closed vent systems. You also might see VCS, which is also a way to look at vapor control system. Those are kind of interchangeable. But as we get into the design and analysis of these systems, we always focus first on the history as to how we got to where we got. And so I'll kind of go through the history, what we're talking about with CVS, get into the EPA consent decrees. If any of you are familiar with consent decrees, they're really, final judgments that have been issued, negotiations through different operators as to how they're going to fix and control problematic facilities or tanks that are venting. And then really getting into the analysis approach. How do we actually build an analysis? What are some things to look out for? And then some of the other factors that should be taken into consideration, from well behavior, steady state versus dynamic analysis, determining a capacity of a system, a couple of maintenance tips, and then what do we do going forward? So won't get into a lot of the details of the actual mechanics, more so the considerations as to how we're approaching this. And so the history, I'm gonna kind of gloss through this pretty quickly. I'm not going to read everything on this. I believe this presentation, or a version of this presentation, will be available afterwards, that you can read some more of the details. But really the history for closed vent system analysis in the US came about in 2002 when there was an APIN, or a permit under the AQCC. So APIN is an air pollutant emissions notice, and so that is actually a Colorado thing. And then the AQCC is Air Quality Control Commission, also a Colorado organization. And so they started this regulation number 3 and kind of kicked off all of these. And so you kind of advanced through and started. Colorado was kind of the center of controlling vapors coming off tanks as far as the U.S. is concerned. And so Colorado started implementing different ozone action plans in the DJ Basin. So that's just north of Denver, if any of you are familiar with the Colorado cities. And we kind of fast forward, and in 2014, Noble Energy got a notice of violation from the EPA, settled with the consent decree, and that kind of sparked the start of all of these CVS design considerations, how we approach it, how the EPA enforces it. And really the idea was to ensure that all the emissions are actually combusted or controlled to some sort of device, a flare, combustor, or a vapor recovery unit. And so basically 10 years ago, 11 years ago is really when this approach had to really start from the Noble Energy consent decree, and all kind of focused in Colorado initially. So we got through all of the consent decree. EPA issued a compliance alert, basically telling the industry that there's a problem, and we want everyone to start looking at these potentially high emission sources coming out of tanks. And as we go into our analyses, we find that they can be quite significant depending on the flash factors associated with these fluids coming into the tanks, as well as just saltwater disposal or water wells can be problematic as well. And so that sparked industry really diving into it. And then basically Colorado in 2018, 2 years after that, or 4 years after that consent decree, started this storage tank work group, which was a voluntary group, and guidelines that you had to, operators could voluntarily control these emissions. So then in 2019, EPA issued a new self-audit program for oil and gas facilities, and that allowed operators to kind of have a free pass to look at problematic facilities without concern of getting notices of violations from the EPA, where they're actively working on it. And basically that started the enforcement of more consent decrees, more CAFOs, which is consent in final order, and these long-term consent decrees. And so now, because of all these things that built up in Colorado as the kind of the epicenter, we now have this enforcement from the US EPA coming out of the DC office, controlling all of these violations coming off tank vents. And basically the agency, being EPA, as well as the regional offices, their position regarding the design of these vent systems on these tanks is that all tanks in CVS must be able to handle kind of the reasonable, foreseeable emissions coming off these tanks. Basically, worst case scenario, all your dumps happening at the same time, all your flash going through your tanks and vaporizing, and all these spikes had to fall within normal operations, or the EPA recognizes that it can fall within normal operations, that it should not result in any kind of relief device happening on your tanks. This would be any pressure spikes, this would be any minor sources going to your tanks, and we'll get into all the details of what these sources are and these inputs. But defining what normal operations is very important as you go through this. Basically normal operation being any foreseeable fluctuations, something statistically viable, although we don't get into probabilistics too much for CVS, as EPA has put quite a bit of scrutiny on probabilistics and question the validity of how probabilistics are determined in the oil field based upon well behavior, artificial lift behavior, and just free-flowing behavior. So basically, our designs now must account for all these potential vapor sources going to the control system. So if they can flow to the tank, or they can flow simultaneously, then we actually assume that they can. And so we're looking at, in many instances, we look at our first pass being kind of the 100-year flood, the worst case scenario, and then we chip away at that to find operational, optimization of how to run these facilities. So sometimes we'll put multiple analyses together. So we kind of put together, okay, worst case scenario, all of our vapor flashes going through tanks at one time, and then we also look at a reasonable operational case that we don't submit to EPA, but we use it for operational focus. So as you get into the EPA, and once again, I said this is very EPA focused, but really that just drives how we look at these things. It doesn't really change the validity of the analysis. It just helps to determine what these inputs are and how to account for different things and how to look at it from a conservative basis. And so EPA came about these Quad O standards, new source performance standards, NSPS, and they started with this Quad O. And that really applied to, a certified flares or control device or something like that, and really dig into the actual CVS. Enter subpart A, so Quad OA, and basically any new modified or reconstructed facility from September of 2015 to before December 6th, 2022. So that falls into subpart A, and it's really a certain criteria. 6 tons of VOCs coming off your tanks in a potential to emit standpoint. So with no control device, if you have 6 tons of emissions, VOC emissions specifically, from your entire tank battery, you're now a tank effective facility, and you have to follow this Quad OA. When you get to Quad OB, which started, the effective date is the December 6, 2022 for new modified or reconstructed facilities, you're getting into a slightly different criteria for determining what the trigger point is. That's 6 tons of VOCs per tank, or per tank battery. Quad OA is per tank. Quad OB is per tank battery, or 20 tons of methane emissions for the entire battery. And so that's where we fall right now. Quad OB has a bunch of other subsets. We won't get into that on this presentation. And then for Quad OC, it's basically existing sources, anything that Quad OB didn't pick up, and it's anything on or before 2022 of December. And that doesn't go into effect, I believe, until 2029 through state implementation plans. So we have some time on Quad OC. But all of these are the basis as to how we approach these design basis. So let's get into the details of CVS or VCS. So what and why are we doing this? So as I mentioned, a CVS is a closed vent system or vapor control system. And basically we're looking at all our inputs coming to our tanks, thermal breathing, so heat and cold loss, whether it be from a seasonal change or from diurnal changes, as well as any kind of capture system, any kind of destruction device. And we're kind of looking at this as a total closed loop system, or a closed vent system. We'll get into the details of a closed loop system very briefly as we go through that. So we're looking at what dynamic behavior, what steady state behavior of our fluids are coming into our tanks, so we can model them appropriate in a conservative manner, and that is in a manner that satisfies from a conservative basis our regulatory requirements, and then also from a slant that allows us to actually operate these facilities within a reasonable parameters. So we're trying to balance 3 different things as we go through this. So through all of this, we say, why do we care? Well, EPA, through all of the history detail that I glossed over, EPA believes that closed tank systems are inherently undersized. And why? Because when they do flyovers, they see venting from hatches, they see venting from your relief devices, and they also see that, many operators, they will permit their facilities, and then the EPA will look at their closed vent system design or their certifications that have been submitted, and they don't match. And so that gives them some question as well. They say you're permitted for 1,000 barrels a day, but your CVS is only designed for 500 barrels a day. Let's explain that. At the same time, as you're designing these closed vent systems, you want to make sure that you recognize that production rate coming from your wells is not necessarily the flow rate coming to your tanks. And we'll get into some of those details, but we want to make sure that we're evaluating what's going to the tanks, not necessarily what's coming out of the ground. A little example, a compressor scrubber in HYSYS or Promax, they're showing that it might be producing just a quarter barrel a day so they spread out that production over the entire day. But in reality, this scrubber dumps for 5 seconds. It dumps all of that production, that quarter barrel. And so for those 5 seconds, the tanks are actually seeing 126 GPM in this example, which would be equivalent to over 4,000 barrels a day of an instantaneous rate. And that's really what we care about, that instantaneous rate going to your tanks. So in situations like this, you find that the overpressurization becomes very common. The EPA recognizes this. And the reason why they recognize this is EPA established all of this in Colorado on the DJ Basin, so north of Denver, in a manner where they have plunger lift. So plunger lift wells are where you get your production over a plunger run, and you might only have 10 plunger runs a day, such that all your fluids are condensed to 10 5-minute plunger runs. And so you get that exact same phenomenon. So EPA, through working through Colorado, established that they knew that these wells could be surging. And so they highly scrutinize how we approach production. And so what we are able to do with these closed vent system analyses is to really determine what's happening in the field, and identify when we can see overpressurization, determine how we establish an operating envelope for a facility. And through all of that, many facilities don't have tank pressure monitoring, but through all the tank pressure monitoring that is installed, we've been able to validate our approach, our analysis, and also establish that we have 95% capture and control, which is what's required by EPA Quad OA and Quad OB. So what is the EPA using this for? And what they want is to say that they tell us that it's proof that you're adequately sizing your tanks for overpressurization. But on top of that, we get some other things where they're looking at, make sure latest industry practices are implemented, targeting big operators to, comply with these high production sites, looking for emission reduction opportunities, which is the charge of the EPA, and also look for opportunities where they can go after for consent decrees and get much more stringent approaches on how they look at it. Really what you want to see as an operator is you want to go through an approach where you can prove all of your design basis, you can prove why you look at certain things, and you can prove what normal operation is, coupled with a robust optical inspection, OGI inspection program, or an LDAR program, such that when you have regulatory challenges, you're able to prove everything that you put in place. So for those of you that know Bluey, you get all this background information, you get all the EPA, and you get all this, and you say, well, why should I care through all this? And that's really the crux of understanding our consent decree or not our consent decree, but our CVS analysis approach is, why do we care about certain aspects and how do we piece it all together? So we get in our consent decrees. I don't need to go through all these in details, but basically this is the process in which EPA provides a consent decree. You get a notice of violation, you get a 114 notice, and that means you're on the track to get a consent decree. And when you get a consent decree, then you have to have all kinds of different things that we've built into our model, such that our models are universally acceptable. They're used for design basis, they're used for certification, and they're used for consent decrees. And we're able to slightly tweak our approach for all of them so that we can satisfy all these cases. So basically, when you're looking at consent decree basis, the EPA really likes us to look at peak potential, instantaneous vapor flow rate, so PPIVFR, if you've ever heard that statement, as well as a physical CVS capacity, so how many million standard cubic feet, or MCFD, could a CVS vent system actually manage. And then also a methodology. For all these consent decrees, the methodologies are determined such that you have to describe exactly what you're doing to the EPA. And through that, that's how we're able to piece together all of these things. The regulatory agencies don't, all the regulatory agencies I've worked with, which is primarily Canada and US, they're not as specific as you'd like them to be. They're not going to say, if you do this, you'll be good. They provide generic approaches. One, because they may not have the technical savviness to actually know specifically what you want, but then also industry lobbies for some of that gray space, so that they have room to engineer and come up with a solution that's not mandated or prescribed exactly, that becomes expensive for every facility, but rather something that's more fit for purpose. And so as you go through this too, EPA's really gotten wise on the minimum turn down too. So they want to look at your PMI VFR, which is your potential minimum instantaneous vapor flow rate. So how much can you turn down your facility? And as you're looking at these consent decrees, and I'm kind of using consent decree for design basis interchangeably through this presentation, we talk, all of our basis now kind of funnels through these consent decrees. And the reason being is because the consent decrees really help us to get an eye into the regulatory agency. As I mentioned, they don't exactly provide forthcoming, thou shall must do this, such that we piece it together through these different regulatory violations that we see. And so when you're designing your facility or your CVS, you want to look at basically two components. You've got a steady state component. So your mass flow coming in is equal to your mass flow coming out. Easy enough. You take your flash coming off your fluid, both oil and water, any vapors going to your tank. You look at any working fluid, so your level coming up and down, and then you look at your breathing losses. That would be from your diurnal cycle, that could be from seasonal changes, that could also just be from heated tanks, and that's your M out. So you have all that coming in, you have it all coming out. And then you also look at your transient behaviors, whether you have plunger lifts, you have intermittent sources, you have compressor dumps, and you want to look at, okay, what's our basically our delta through the delta time of all these inputs coming in. And so we want to piece those together. And so when you look at the steady state component, you can compare that PPI-VFR, that peak potential instantaneous vapor flow rate, and you look at to the tank capacity. So in this situation, you've got a steady flow, so you'll ramp up and you'll steady flow. So those are all your mass inputs, and the red would be your capacity in this case. So typical steady flow systems would look like this. However, in reality, you'll see some of these transient behaviors too. So in a transient system, so these would be your minor sources, intermittent dumps, plunger lifts, different things like that. You'd see that you've got a much more erratic behavior. So you can't actually look at a PPI-VFR, that peak potential, because it's all over the place. If you looked at your opportunity to hit having all these intermittent dumps happening at the same time, then you'd have this gigantic amplification and it would blow up your system, and the only way we could solve it is with 20-inch vents on the top of our tanks, which is extremely unrealistic. And so this probably is closer to reality of what we really see, but this would be, is very conservative based upon that there's no baseline input assumption. So in reality, what do we really see? Well, we really see both. We really see that the pressure in your tank is very dynamic. It's based upon what's coming in, what's going out, what's going to sales, what's going to trucks, ambient influences. And so we kind of get a combination of both. And this is what a pressure trend would look like probably in a reality situation where you get those tight bands. You're able to see, that's more of our steady state component. That's our constant in, constant out, where we can model as that single curve, right? But then you get these big spikes, and they're amplified based upon where they hit, such that you're seeing that dynamic behavior. So how do you approach this? How do you really look at it? And that's really what gets us into the meat of how do we actually CVS, how we build these vent systems. And so we basically pile on a lot of different things. So we've got all our theories, our codes, pressure drop theories, fluid dynamics. We look at the different thermal breathing theories, whether it be API 2000, whether it be AP 42. We look at equation of state models through ProMax or through our own equation of state modeling. And then you pile on all the codes and standards on top of that, ASME, API, NFPA. And you layer these all together because there's no engineering codes or standards that prescribe which flow theories to use for tank CVS. Flash theories are very different from normal pressure, higher pressure systems to these vapor systems, these systems that are at fractions of PSIs. And so that's why we had to build this design analysis layering all these things together. And the classic, if you ask 100 engineers, you've got 100 different engineering approaches. Well, just like we have about 25 people at Valor, you ask the 25 people, everyone's going to have a slight different approach on how they do it. But what Valor does differently, and what we bring to the table that helps us to understand the CVS, is that we're able to take all these theories, all these codes and standards, and then we'll layer on the experience. The experience being validating all these models to the field. Models are only as good as their inputs, junk in, junk out. We have all these regulatory nuggets, consent decrees, CAFOs, all these notice of violations that we're able to piece together through our clients, that we're able to pile on all these learnings and say, okay, from a regulatory standpoint, this is really how we need to be looking at, because this is how it's being scrutinized. Or we say, well, in reality, we actually are matching our tank pressure data to our model, and our model is overly conservative. We can actually back down on our flash factors a little bit to line up and calibrate our models. And so that's one thing that we really hang our hats on, is that these models are only as good as you can prove. And that's proving through the regulatory agencies, but more so proving through field data. Our goal is to kind of keep our clients out of the ditch and producing, such that we want to design something that's reasonable, that's economically viable, as well as putting together a defensible analysis, because this is all anchored in theoretical modeling. And I always throw in my old you may not know this reference. It's an old Tom Cruise reference, but it doesn't matter what we believe in our CVS. It matters what we can prove. And that's really how we approach our CVS. And the reason for that is you might have a recirculation pump that's pulling off your tank bottoms, that's taking bad product, if you will, or out of spec product, most likely high water content, and sending it back through your treatment system. Well, that as that recirculation pump turns on, it's going to get a slug of water. How much? I don't know. It depends on how bad your separation process or how inefficient you've been operating. After you get all that water off, you're going to get to dead oil. So oil that's already flashed down to atmospheric. I don't know how much that's going to be. And so how do you model that? Well, we don't know. We have to look to what Tom Cruise says and say, well, what can we actually prove? Well, in that instance, we say, well, we're going to take the more conservative approach, because we know it's not this bad. But unless we put meters on everything, which is unreasonable in the oil field, we actually can't put things together. But we can point to the worst case scenario. So what are the three questions then as we go through this? Is what is your goal for this analysis? Were you compliant before this? Did you already pre-design it and you're just validating that we're bringing more wells on? Or are we just validating that our design still matches? Do you want to evaluate, are you compliant today? Maybe this is a facility that's already built and we're doing a post-appraisal, or we're doing a true greenfield design for being compliant in the future. And all of this CVS is very much, from a regulatory standpoint, based upon a risk mitigation. But even in practice, we're de-risking the chance of venting. We're never going to be able to prove it, or control exactly what's going into the tanks. We're never going to actually model in a reasonable manner what's going to the tank, what the flash is coming out, what the product's coming out of the ground, that it's consistent from month 1 to month 2. But what we can do is establish a basis, so that we say, hey, we have it set at this pressure. We're going to run our analysis at this. We're setting it at this production rate because that's the most we've seen in the last 12-month period. Perfect. We define all these things such that we have that lined out on how we approach this. There's a lot of knobs on a CVS design, and you need to identify ways to control that. So, as we're going through an analysis approach, I probably have a lot more slides than I can talk to today in this webinar, and I want to make sure we leave time for questions. But these are the main considerations you want to keep in mind when you're looking at a closed vent system, which is your well behavior. What kind of artificial lift do you have? How many stages of separation? So basically, do you have a constantly flowing well? Do you have an intermittently flowing well? Are there surges? Can we predict those surges? How many stages of separation do you have? Are you going through a single stage of separation, or we have multiple stages that are actually smoothing out that flow a little bit and also pulling off that flash coming off that fluid. So that helps to determine, should we do a dynamic or a non-dynamic model. We want to look at the valve behavior. We want to look at these dump valves. We want to look at trim sizes so we can determine, is there choke points that can restrict through choked flow our fluid, so we actually know, hey, we might be producing this much, we might be producing 150 GPM of production, but these valves can only flow 50 GPM through them. And then we want to look at the GFD, which is our governing flow device. Which device through your separation process controls the flow behavior going to your tanks? If you have on the front end, your first stage of separation, you have these big snap acting valves. So basically a valve that opens really quickly and you get this surge of fluid. Most often you see that on the first stage of separation because most of the flow meters in the oil field actually need a constant flow. You can't have a throttling flow through that to get accurate metering. And so you have this big snap valve so that you can get that flow measurement. And then your secondary stage, maybe that's a throttle valve. It just opens as fluid comes in. Well, that governing flow device would basically be that snap valve. That's what's dictating the behavior that's going to be going to your tanks. And then you want to look at your minor sources. Minor sources are not insignificant sources. Minor sources are intermittent sources. So basically not your main production, but your compressor dump valves, your sales scrubbers, anything that might have high levels of flash, high levels of pressure, but are not necessarily predictable from a constant operation basis. It happens a few times a day, but you don't exactly know what, because we don't instrument those. And then you can look at your peak minimum, your peak potential, and look at what all these influences are in capacity. Are there any operational considerations? And layer these all together to actually get what your capacity determination is. So we kind of talked about, non-dynamic and dynamic, but typically with non-dynamic, we want tank pressure monitoring so we can keep ourselves out of trouble. As we're looking through this, then we want to look at your stages of separation. We want to determine, okay, how many stages are going through, how much flash are we able to take away? So in this situation, you got your inlet separation. So that first stage of separation, you got your water going straight to the tank. So whatever flash is in that water, whatever vapor entrainment or gas entrainment's in that water, it's whatever is at that first stage is its peak potential. And then each level of separation will pull more gas off and send it to sales. So then we can determine, okay, what's the maximum amount of flash going to the tanks? In this situation, it would be the heater treater that's going. And we want to also keep track of what the limitations of steady state might be. That steady state model, that flat curve, that is basically your mass flow versus your mass flow in equals your mass flow out. And for a non-dynamic analysis, it assumes that you're getting a steady flow. What's coming in is going out. And so you can kind of look at this chart here where you've got different types of wells: free-flowing, gas lift, plunger lift, and then the stages of separation. And we really want to be operating in the green in terms of how we model, but we can, with some conservative inputs, model the yellow. We want it to be near steady or steady. But then you look at non-steady operations, so limited stages of separation, highly dynamic fluid loading from your well, and you really can't look at it from a non-dynamic basis. You need to actually do a dynamic analysis. The next major component would be your thermal breathing. So that is basically that diurnal cycle, the heat loading on your tanks, whether you have heated tanks. And US EPA kind of has provided multiple ways to look at thermal breathing that they really focus on, which would be AP 42, it's API 2000, and API 12F. And you can kind of see on this chart, breathing loss versus tank size, wildly differing methodologies. The most standard as of now for US EPA is to look at API 2000, and you might have a CVS has zero production going to it that might fail on a thermal breathing basis because that's such a steep line. And really what this comes down to is engineering judgment, field validation, because we know thermal breathing is not going to be AP 42, basically zero, which is an older legacy approach for EPA. And API 2000 is highly unlikely. That's extremely conservative. But if you run API 2000, our regulatory agencies will accept it. but it might require drastic oversizing of your control device or your vent system. We know it's going to land somewhere between those two. And that's where the field data, tank pressure monitoring, and validating your model to what's happening in the real world is absolutely crucial. The other consideration for designing your CVS is looking at your production rate. I mentioned, that instantaneous flow rate versus normal production. You look at your production curves in this is, the data coming in from the wells, and you're seeing that, it looks pretty steady, but if you zoom into that flow rate, you actually see significant spikes throughout the day, a pretty decent instantaneous flow rates. So that's, it's, I don't know if you guys can read it, but it's expressed in barrels per day of oil, and you'll see spikes at 1,000 barrels a day. But when you kind of average it out, it might not be that high. And so we want to make sure that we're taking the most conservative way to look at it, and also what the reasonable amount of fluid coming in your tanks is, not necessarily what's coming from your wells. And looking at this, if you leveled it out, you can actually create a steady state model based upon this flow rate if you properly pick your production levels, such that you can actually see for 12 wells coming into this facility, that's that top right chart, that's the real pressure curve, and the bottom is a steady state curve. So just because we're seeing this really erratic behavior, you can represent it in a manner that's steady state and matches reality. Coming back to the field validation. So how we actually determine all our inputs for our design basis is looking at production, EPA regulations, and pressures. And I'm going to really kind of jump through and start looking at some capacity determinations on how we actually look at it. So that's the crux of all of this. We want to identify what our inputs are, but we also want to determine how do we actually calculate what our CVS capacity is. And so throughout your system, you've got multiple components of your CVS. You've got your wellhead coming into some type of separation, multiple stages of separation, with dump valves that are being controlled by level. And those are going to your tanks, they're going to multiple stages. From your tanks, then it's going to your control device, your enclosed combustor, a VRU, or a flare. And then we want to break down how we're actually evaluating our tank system. So you've got our vent for the tanks highlighted in red. And we can kind of sum up, okay, where do we want to actually evaluate this analysis from? Well, really, unless you know exactly which tank, usually your operators will select different tanks. They'll fill a tank and then they'll switch to another tank, or there's different strategy on how they operate. We don't always know which tank we want to use. And through low pressure flow theory, that makes a big difference. The tank at the end of that vent will have far more back pressure to go than the tank right before it goes to your flare. And so we'll want to pick the furthest tank away so that we are modeling from a conservative basis, unless you know explicitly where fluid's going all the time. So we want to model our furthest tank away, and kind of like to break it down into multiple components. Now, this isn't required mathematically, but we like to break down the tank headers into systems so that we know, okay, where are our bottlenecks? And it helps for diagnostics, it helps for determination of where we need to focus our efforts. We might have a giant flare that's way oversized, and our tank headers on our tanks, the main tank header is undersized. Well, if you built it as one full system, you wouldn't actually know where that bottleneck is. And so we like to break it down into manageable bites so we can actually diagnose where it's coming from, where those bottlenecks are coming from. The next thing is to look at our flares or our combustor systems, and we like to express that in terms of an equivalent length of pipe. So we base that upon a manufacturer curve, something like this, where we're actually able to look like, okay, what is the maximum relief device that we see? Let's say that our minimum relief device is set at 10 ounces, then it will probably start cracking around 9 ounces. So let's do our design base at 8 ounces. So we look at what that maximum flow rate is for a flare, and then we convert that into a equivalent length to determine what that capacity is. Also, as such, we are looking at all of our pipes and fittings. looking at friction factors, looking at valve capacities known as CV, and piecing this all together so that we have this from the tank size to your flare or your control device. We're looking at the entirety of this many equivalent length. We use 3-inch, but you could use whatever equivalent length you want. It just needs to be normalized, so you're talking apples to apples for each segment. And for your capacity determination, we want to look at what is the equivalent length actually mean. Well, in this is a enclosed combustor. We've got 150 feet of straight 2-inch pipe, has the same pressure drop of 1,040 straight 3-inch pipe. So you can kind of see the difference between a 2-inch and a 3-inch. When you look at this combustor, we've got this little flame arrestor here. This little flame arrestor has the equivalency of 118 feet of 3-inch pipe, which is a 30% reduction in capacity. So you might have a hugely oversized vent coming off your tanks, but you have that little flame arrestor in there, and you add 110 feet that you might not, or 118 feet that you might not be accounting for. So we want to always look for these bottlenecks and want to make sure that we're not oversizing something and then shooting ourselves in the foot by putting a too restrictive of a flame arrestor on. Here's just some other examples of how much equivalent length we might have through different fittings. So you have, the sharp exit from your outlet. You've got all your pipe. You add that all up, and you've got 640 feet, even though you actually only have 400 feet of actual pipe runs. The other components that we want to be looking out for would be our model accuracy. We want to take that blue line, which is our model tank pressure, and actually go and compare it to the field as we're able to. We do this in many cases where we actually take mobile meters, mobile pressure gauges that are logging, and go to a field and actually test through different scenarios to validate our model. And the goal is to get really good alignment. This would be A+ material in terms of alignment of a model to actual field data. So as we go through this, there's tons of lessons learned that you want to take into account as you're designing a closed vent system and looking for systems or components that cause significant pressure drop for the vent system. So these are little Inardo 800 series inline vents, so it's got a weight on it and it allows flow. Well, these have extremely high pressure drop. Those tend to be for a 4-inch, about 300 equivalent feet of 3-inch piping. I talked about these flame arrestors. On combustors, you'll have multiple rails, sometimes multiple burner rails, and each rail will have its own flame arrestor. And you can see the different flame arrestors have different equivalent lengths and can significantly cause back pressure. As well as vapor recovery units. Vapor recovery units are extremely difficult. My initial background for facilities engineering was on rotating equipment, and so I can speak firsthand that compressors and vapor recovery unit compressors are very dynamic and are very complicated to model. They are based upon what your speed you're running at, what your capacity of your compressor is, where your unloading devices might be set, as well as what your suction and your discharge pressures of that compressor. So they're very hard to describe, and so testing becomes absolutely critical for VRUs because you can't really express them in terms of equivalent length. You can express them as a capacity. So you want to be very careful into how you actually represent that as a capacity, and really lean on your design basis when you're modeling a vapor recovery unit. The other thing that happens a lot in the field is you'll have a dual tip flare. You'll basically have a high pressure system and you'll have a low pressure system coming into your flares, high pressure being your relief devices. And you'll share different components of it. You'll share your pumps, your knockouts, and that can cause quite a bit of upset to your tank system, where you actually have higher pressure going back to your tanks and resulting in overpressurization of your tanks. For any kind of pneumatics, we want to make sure we're accounting for those vapors and actually calculating what the vapor is going to your tanks from those pneumatic devices, whether it be in pneumatic pumps, pneumatic valves, you name it. And then also whenever we're designing a CBS, we want to look for pocketing. So in this situation, we're going to get a ton of liquid loading on this flame arrestor going to your flare, and that's going to reduce capacity, as well as you have a very hot environment. It's probably going to lead to caking and coking of your flame arrestor and reducing its capacity, in which you won't be able to get alignment of your model to your to what's happening in the real world. And then lastly, you want to kind of look at where you're actually measuring your pressure. In this situation, we've got a pressure gauge that is right here. This I don't know if you can see my cursor, but there's a blue head in the right corner of the screen. That's your pressure gauge, and upstream, that red device is a control valve. So you're controlling the downstream of that valve, which you're not going to actually seeing what pressure is going on in your tanks. You're going to be seeing what's going on in your flare, and that's not going to be adequate control. So that's kind of the considerations when you're actually sizing your vent system itself. But it's not just about your vent system, it's also about your inputs. And so we want to look at all these different processes. And let me jump forward. This is an example of the inputs to a tank system and how we're trying to simplify it into, whether it be steady state inputs, minor sources. And so we're taking these pretty complex with high and long levels of piping, lengths of piping, all kinds of fittings, and condensing it into a reasonable model. Some other inputs we want to take into account are water. When we're sending water and oil to a tank, water, we often call it the silent killer, because you have 1 to 4 standard cubic feet per barrel that can be in the water stream. And where high water production, high water wells in the Permian Basin, the Delaware Basin in New Mexico has very high water cut rates. Tend to be, water production tends to outpace oil production, in which case this could cause a significant overpressurization of your tanks from water, which can be something that you're not thinking about. This is also talking about your instantaneous flow rate. We don't need to talk about that, but basically all your instantaneous flow rates, we want to know what your dump duration is and what the fluid is during that dump duration, so you can extrapolate that, especially if you're using a steady state model. You want to extrapolate that such that you're seeing that instantaneous flow rate. The other thing is we want to be cognizant of any high pressure dumps, high pressure sources that go directly to your tanks, because not only do we need to be conscientious about vapor flash, the liberated gas as you're dropping your pressure from, you're operating 150 psi to atmospheric, but you also have motive pressure when it comes to compressor scrubbers that are running at much higher pressure. A discharge scrubber on a compressor could be 1,000 psi, might not have any flash really associated with it, with the water dropout, but it has a lot of motive pressure that we want to make sure we're taking into account. And then kind of two high level flash items would be H2S scavengers. We find that H2S scavengers extract your hydrogen sulfide, but also brings a lot of flash. It has a high affinity for natural gas, these mediums, triazine, or the chemicals, such that when you are dumping that spent fluid to like a slop tank, chemical tank or whatever that shares that same vent header, you can actually have really high levels of flash. Typically for oil, we're seeing 50 to 150 standard cubic feet per barrel of flash, and then 1 to 4 standard cubic feet per barrel of water flash. You get to these H2S scavenger, and you're seeing 1,000 to 1,500. We've seen as high as 5,000. And so could be a very problematic area when you're designing. And then lastly, not lastly, I guess I got maybe one more, is our truck loadout, especially water truck loadout. So if any of you are familiar with how water trucks load out at an oil facility, they'll pull up to a site, and they'll actually have a vacuum pump pulling on your trunks to increase the rate at which they're pulling fluid from the tanks to decrease their time sitting on the pad. But they do a vapor bounce back to the tanks to balance out that tank, so they're not venting hydrocarbon that's with that water, such that you're sending a huge rate back to your tanks from that vacuum pump. And that can cause a significant overpressurization. It tends to not be combustible, but as soon as you open that tank, you're going to be letting all your oil flash come off as well. And then lastly, sales gas scrubbers can have highly volatile fuel because of all that gas in there, and the water dropout is going to have it's got a high affinity for gas, and it's going to have a significant amount of flash. So I'll try to wrap up with a couple more slides and get a couple questions in there, but we also want to take into account maintenance. You saw that pocketed picture with the flame arrestor. That might be building up fluid in there, might be coking up that flame arrestor, but we want to make sure that we're properly managing all the items too. Our analysis doesn't take into account poor maintenance. And so you might build the perfect CBS system, you might have it oversized, or it might be just perfectly optimized, but without proper maintenance, you'll still likely be venting. And so this becomes very difficult to manage a closed vent system with actual operations. So data is king, pressure traces is king. You can kind of see on this pressure trace, this is a tank pressure monitoring, where it's starting to climb, and then they perform, different maintenance, and look at it comes right back down. So understanding that a closed vent system without proper maintenance is not going to actually control your vapors. So, kind of to close is, how do we use these analyses? We want to make sure that we're building defensible analyses with a lot of conservatism, but we also want to make sure that we are doing it in a reasonable manner to evaluate the risk of regulatory pressure. So we're evaluating with full tanks, we're evaluating at the most conservative production numbers, and we want to have justification in that design basis for what we're doing. And a lot of our design basis, we leverage the US EPA. US EPA likes to look at the 95th to 98th percentile of pressure, temperature, and tank levels. They want you to take new samples so you can actually build, use equation of state model to actually determine what that flash is coming off of that. They actually want you to do leak testing where you actually pressure up your tanks. So you've got a relief device set at 16 ounces, but it starts leaking at 14 ounces. That's extremely common for thief hatches, such that we want to actually measure where it starts wisping out gas a little, so then we can do our design basis below that. And we also want to look at, whether it be API 2000 for thermal breathing, or we want to actually look at what our test data shows. So we want to take all of these things and build a model that's operational. So we don't want to just, everyone can go out and build a huge vent system, but it costs money. And doesn't yield a return. So we want to make sure that we're balancing that optimization of operability, economics, and regulatory compliance. So, I'll kind of close with this is, as we're going through the closed vent system analysis, we want to really focus on these critical parameters and what's verifiable, whether it be through field observation, or when I was giving the example of a recirculation pump that we know it's not going to be full oil, but we don't know and we can't prove what it is. So identifying these critical parameters that are provable or are conservative enough that they're an accepted practice. And then through all this, we always want to look at what the data says. Tank pressure monitoring is absolutely critical to validate our models. And we don't need tank pressure monitoring everywhere, but we like to actually validate models so that then we have confidence when we apply it to the next one. So hopefully that was a little bit of insight, very high level. I would say that tank CVS design is pretty easy from a mechanics standpoint. What isn't easy is that it's not a straight shot on how you do it. It's very nebulous. There's a lot of gray space. And so, to actually, I've been doing closed vent system design as a subset of facility engineering for about 4 or 5 years now, and I'm still just scratching the surface on all of these assumptions and how to piece together a very fluid and nebulous operating area. So with that, I'll open up for questions and see if I can answer them, or if you can stump me.
Thanks, Mr. Rizowski. Yes, there's a lot of important piece information. Thanks. I have a question. about the CDS. What best practices exist to prevent overpressure or backing events in the water tank connect to CDS?
Yeah, so the best practices is to understand what your requirements are for your inputs to start with. The inputs being what are your criteria for establishing what kind of dump valves you have. If you can do throttling valves, you're able to smooth out that flow a lot more. But if you have metering requirements, then you'll know that, okay, we need to have multiple stages of separation. Some other best practice would be oversized venting, as well as the straightest shot vents that you can, limiting your valves, limiting restriction points, and also probably one of the biggest things we see, the biggest restrictions would be sizing control valves like you would in a normal facility, where you can actually have a 4-inch line that you bring down to 2-inch for your control valve because it's a short run, and so you don't get the huge pressure drop. But in these extremely low pressure, these vapor systems, you can't design it based on that. Sometimes you need to go the opposite way so you're not creating a restriction in back pressure. So it's all about understanding where your pressure buildup is.
Okay, perfect. Mr. Lisowski. Another question. Is there any states in US that have more stringent rules than EPA does?
That's a great question. Yes and no. US EPA is a federal over all the United States, but then each state has their own jurisdiction where they can actually impart their own rules. For the most part, for tank CVS, they're all about the same. The most stringent above and beyond the EPA would be Colorado and New Mexico. New Mexico follows pretty close to that Quad OB federal rule, US rule, but Colorado puts their own flair on it, especially because they're the ones that kind of pioneered it. So like Colorado will say that there's no active flaring. So you actually have to build a closed vent system. You have to put a control device on it, but if you are overpressuring, you must shut in. So it's only for emergency basis is what those flares are for. So most states will put a little spin on it. As you get to that Quad OC, that's that new regulation that's being implemented in 2029 or affected. Those are going to be run through state implementation plans. So 50 states, we don't have 50 states that produce oil, but all 50 states would have their own implementation plan. And so you're going to see quite a bit of variation. There's also been instances where US EPA will see a problem and they'll tell a state, if you don't control this, we will. And so that's when you'll see states come in and actually implement more stringent rules because they don't want the federal government stepping on their toes, and they will actually put something above and beyond just to make sure that they're still maintaining their control.
Perfect. Another question by Andres Quintana. Can push gas eliminate the need for a flame arrestor?
Can you repeat that? Are you asking about maintenance for the flame arrestor?
Can push gas eliminate the need for a flame arrestor?
In many instances, no, and that is because in many instances we're using deflagration flame arrestors, and so it's based upon your proximity of your flare to your tanks, the risk of blowback, especially for or burn back, and it's based upon your pipe sizes that determine that whether or not you can actually do that sweep gas or not. In high pressure relief systems, you can get away with not having a flame arrestor given certain circumstances, but for those low pressure, you've got a high risk of burn back even with that sweep gas.
Perfect. Thanks. And the last question is about what quantifiable environmental or economic benefits have been observed from deploying CDS in upstream or midstream oil and gas facilities?
That answer, it's my classic answer of it depends on a lot of factors. In the oil field, for instance, the Permian Basin in Midland, Texas, the economic benefit is pretty minimal, and the reason being is for closed vent systems. The reason being is there's not a whole lot of natural gas infrastructure to do something with that gas, and so it becomes very cost prohibitive to actually collect it at these low volumes, compress it, and send it through low pressure compression lines, or the lines may not even exist. And so that's why in Texas you see a lot of flaring, is because there's no infrastructure. You move up to areas such as Colorado, North Dakota, and they've actually built a lot of infrastructure so you can actually capture that gas, and it could have pretty decent economic benefit depending on how much flash comes off that. To give you an example, in the Permian Basin, I was working on a facility that was producing a ton of fluid. 10,000 barrels of oil a day, and they were producing almost 2 million standard cubic feet of gas a day in tank venting in that flash liberation. There was no pipeline to send it to. There's no place to do anything with it, so they were actually combusting it through a big flare. But that would have extreme economic benefit because of how much volume was coming after it. So it really depends. It depends on that infrastructure, and it depends on how much gas it's producing, and it depends on how much it costs to run those VRUs. That's a great question, though, and there's definitely tons of opportunity to actually monetize the benefit of these closed vent systems.
Okay, perfect, Mr. Lisowski. We don't have more questions.
Okay.
And we sincerely thank you, Mr. Lisowski, for this valuable presentation and technical insights. And we extend our appreciation to all attendants for joining us. We hope this session has contributed meaningfully to your professional development. Please stay connected with ASICPET throughout our communication channels to receive updates on upcoming webinars and training opportunities. Have a great day, and we look forward to seeing you again soon. Nice to meet you.
Yeah, thanks for inviting me, and hopefully that was beneficial to everyone, and feel free to reach out with questions.
Okay.
All right. Thanks so much.
Have a good day.
You guys too.
Mr.